gone and closed the door. So I won't be bothering people up and down the hall. I'll just be bothering y'all. Okay. We are now recording. I know there must be some announcements out there, but I saw a few on emails, but I was not connected to a printer, so I couldn't print them off. And then yesterday I tried to get to them and kept running into emails that were demanding I do various things, so that ate up my whole office hours yesterday. Let's talk about what we've know about this class. Okay? We're going to finish 2.6 very quickly, soon, I hope. And then we'll move to chapter 3, 3.1. We're not doing 2.7. So that means on Thursday we will have your test on chapter 2. We'll cover 2.1 through 2.6. Your quiz covered quiz. Oh yeah, quiz. There was a quiz, wasn't there? That a bunch of people haven't turned in, have they? Okay. I need those quizzes in, folks. There's a lot of blank space on my grade column for the quiz. So please get your quizzes in if you haven't gotten them in already. Okay. Kiara? So, I need those quizzes in. And while we're on that subject, research papers, which were assigned at the very beginning of the course, and right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9 out of my 38 students. That's less than a quarter have turned in the research papers. So please, folks, you only have a few weekends and Thanksgiving week to work on those, so please get them in as soon as you can. And while we're there, quiz 1. Okay? So I have 1, 2, 3, 4, 5, 6 people that haven't turned in quiz 1. Now, one of those withdrew, so scratch that one. But several others, I do not even have your quiz 1. Of course, if you haven't turned in quiz 1, that means you haven't taken test 1. So, at least that many haven't done that. Now, a few have taken it, but I wasn't sure if you had... Got it. Okay. I wasn't sure if you were through or not, so if you don't see your grade on Blackboard, that means I wasn't sure if you're finished with your test or not. Of course, if you haven't taken the test, I'm certain you haven't finished your test. So on test 1, I still am missing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, 15 or so test 1s. All those people who didn't turn in quiz 1, I know they haven't done it. And then, yes. Anytime you want to during my office hours. Okay? And so please get those completed. Because, and then like I said, only a few people have turned in quiz 2. And those, you need to have those in before you can take your test. And the test will be Thursday. So please get your quizzes in. Otherwise, instead of taking your test on Thursday, you're going to have to be working on the quiz. Or, I don't want this to happen, but it could if you choose. If you asked me to give you a 0 on the quiz, you asked me politely and nicely, I have to say yes. So I don't want to do that. So please get your quizzes in before Thursday. Preferably today or tomorrow, so I can get them graded so you can see what you missed on the quizzes, because about the first half of the test is going to be on the same material, not the same questions, of course, on the same material as the quiz. So please get your quizzes in soon, okay? Now, let's talk about the rest. We're going to finish chapter 2 today, start chapter 3. Then we have the test on Thursday, and then bad news for you guys. Thanksgiving week, you don't even come to school. Okay, sorry about that. We'll be here. The school will be open Monday, Tuesday, and Wednesday. Okay? But it will be closed, of course, on Thursday and Friday. Yeah, question?
I finished my test. There's no grade in that board. I just want to finish with it.
You are finished with it. Okay, so that grade you want down there. Okay, let me do that real quickly. It won't be a blackboard now, but I'll put it in the grade book. Let's see. Huh. All right, it will be in there. Maybe today, maybe later. Yeah. Okay. All right. So next week, you're off all week. We're not. We've got meetings Monday and Tuesday and office work on Wednesday. Now, let me clarify that a little bit. Some will be going to Montgomery. There's statewide meetings going on in Montgomery. I'm not going to be. Now, just because I'm going to be on campus does not mean I'll necessarily be available, because they usually have meetings for us Monday and Tuesday. So we'll be tied up on the Birmingham West campus. They're going to tie us? No, I'm sorry. On the Birmingham West campus in meetings most of Monday and Tuesday, or that's what they've always done. Then Wednesday, they let us come back to the offices. So I will be in the office at least Wednesday morning, okay? Now, if you have business to do with the college, try to get it done Monday or Tuesday, normal business hours, or Wednesday morning, because it's not necessary. It doesn't always happen, but quite frequently, Wednesday afternoon, the day before Thanksgiving, they'll let people go home early, okay? It's never guaranteed. They never let us know if they're going to do it or not, but most of the time, they'll let us go home sometime after Amari comes in. Not me, okay. Afternoon. It won't necessarily be at noon. Sometimes it's 1, sometimes it's 2. Sometimes they may not do it at all, okay? But I wouldn't come into an office Wednesday afternoon and expect to find it open. You may luck out and find it open, but the odds are it won't be. Wednesday morning, sure. I think all the offices will be open Monday, Tuesday, and Wednesday morning, but I do not bank on it being open Wednesday afternoon. Like I said, it may be. I'll probably be here after they say go home, but you can't bank on how long that will be either. Okay. Then we come back after Thanksgiving, have one more week of class, and we'll continue in chapter 3 then. And then after that week, we have our final exam. Now, ours is scheduled for, I think, Tuesday morning, and I think during finals. And I don't know why they do this, but they do. They go back to the 8 o'clock. I don't know if any of you were here. We used to start classes at 8, not at 8:30. But whoever does the final exam, they didn't get the memo, okay? They still are scheduling finals at 8. So the odds are this will be scheduled for 8 o'clock that Tuesday morning. I'll be here, but I'll be here all day. So if you don't get here in time, I'll be here all day. Now, the room may not be available all day, but I'll be available all day. So deal with that. All right, let's end that. All right, any questions before we get started on finishing chapter? Yes?
So you will be here next week?
I'm sorry?
You will be here next week?
I will be on the Birmingham campus, probably Birmingham West campus, Monday and Tuesday of next week, but I'll probably be in meetings most of those days. I can't say if it's going to be all day. I don't even know where they'll be. Most of the time in the ACAP building in that theater down on the first floor. That's where they usually have us Monday and Tuesday, Thanksgiving week. Wednesday, I'll be back on this campus, but I don't know how long. I'll be here Wednesday morning at 8. I'll know I'll be here through noon, and I'll probably be here into the afternoon, but how long, I don't know. Because actually sometimes when they close the camp, when they let us go, the police come around and say, we're locking the building, so I have to leave. So even if I wanted to stay late, I may not be able to. Not that I won't do that much, but it could happen. But yeah, I'll be on this campus Wednesday. I'll be on the other campus probably. Now, they never let us know the schedule anytime in advance. Not even whether Karen comes in or not. Okay. And so I don't know what their plans are for those days. But most of the time it's been, in fact, just about always it's been on the Birmingham West campus and the ACAP building. Did you need to see me then, you think?
I was trying to see when you're gonna be available next week, just in case I couldn't take my test Friday.
Okay. Well, I know I'll be available Wednesday morning. Oh, let me say this too. I almost forgot this. I have an eye appointment Monday morning and Tuesday morning at Eye Foundation Hospital. Monday, they said it'll probably be about 3 hours. Tuesday, they said it won't be very long at all. So it's a follow-up thing for the procedure they're doing. So I won't be there first thing then. Now, I can say this. Usually, they let us go 4:30, something like that. I can stay late then. Do you know where Dr. Pruitt's office is? Okay. Do you know the academic building, that long B building, B hall? Okay. The very last room on the end toward the baseball field, the gym, and the tennis courts. When you go up that half flight of stairs, when you step on that top rung, there's a door right there to your right, B122. That's Dr. Pruitt's suite of offices. I'm in the copy room behind the secretary's desk. So if you want to meet me there one of those 2 days, I'll try to be there. So will you let me know either Thursday or Friday? Okay. All right. Any other questions? All right. Sorry this is taking longer than I intended, but glad you're getting your questions answered. So let's go from current slide. And we were going to do example 6. No questions, anything before example 6, right? All right, let me get my pen set up. Okay. Now, sketch the graph of f of x is equal to, didn't we start this one last time? Say again? Okay. X squared, I remember, yeah. X squared minus 9 over x squared minus 2x minus 3. Okay. We really don't need those parentheses in the denominator. They don't hurt anything, but they don't add anything. And here's Jeremiah. All right. Okay. Now, y'all fill me in real quickly. What do we do on this one? How do we proceed? So anyone who wasn't here last time can pick up where we left off. What's one of the first things you'll do? There's several options, huh? Okay. How do you determine the domain of the function? That's one option you can start. Certainly fine. What is it that limits the domain of a rational function? Now, let's back up a moment. Polynomial functions, what's their domains? All real numbers, always. But rational functions, you're limited. What could possibly limit the domain? Because a rational function is a ratio of two polynomial functions. So why wouldn't it still have all real numbers? What's the issue? you have in a rational function you don't have in a polynomial? Say again? Well, you do have a ratio. What part of that ratio is the problem? The denominator. And what is it about denominators? They can never be zero. So, one of the first things we'll want to do is, how do we determine what would be the zeros of that denominator? Factor it. Excellent. Okay. Does it factor? Okay. How does it factor? X minus 3 times x plus 1. Okay, that tells us right now that x, you tell me what it tells us, cannot equal 3, and x cannot equal -1. Perfect. So we know the domain is limited by anything to the left of -1, from negative infinity up to -1, can't have anything there. Then from -1 to 3, you can have values there, but not at the end. And then from 3 to positive infinity. Fine. All real numbers except for those two. Okay? Now, so we determined domain. What's next? Oh, I'll write it down. Domain of this function is negative infinity to -1 union -1 to 3 union 3 to infinity. All real numbers except -1 and 3. What's next?
Is that how you want us to write it on the test?
You don't have, if I ask you for the domain of a function, yeah, that would be a good way to do it. There are other ways you can do it. You can write it in words. You can just say x cannot equal, okay, this right here is perfectly fine. This right here is perfectly fine, okay? You can write it all real numbers except x equals -1 and 3. That would be fine. There's lots of ways to do it, okay? You can do it in set notation. The set of all x's such that x is not equal to -1 or 3. Lots of ways to write it. As long as I understand, you understand that those are the two excluded values. All other real numbers work, okay? What's next? We determined the domain. And say again? Okay, we want vertical and horizontal asymptotes. Okay? Let's start them here. Let's start them over here. Vertical asymptote. What's going to be true about a vertical asymptote? Now here we're going to get into a little bit of problem if we don't do something else first. Factor the numerator as well. In fact, I suggest one of the first things to do, factor everything in sight. Now, it's not necessary to be the first thing, but at some point. So how does this numerator factor? X minus 3 times x plus 3. Now what do you notice? X minus 3 divides away. Now, does that mean that x equals 3 is now part of the domain? No, because it would still make your denominator 0. But what it does mean, x equals 3 is not a vertical asymptote, but x equals -1 will be. So there's your vertical asymptote. X cannot equal -1. You have to keep in mind x can't equal 3 either, but this is a vertical asymptote. The 3's went away when you factored out the common factor. Next, you said horizontal asymptotes. What's going to determine your horizontal asymptote? Say again? Ratio of the leading terms, is that what you said? Excellent. And what is the ratio of the leading terms? 1. So y is equal to 1 is your horizontal asymptote. Okay? In that case, I would have done that before I factored, but you can still do it now because you can still see your function. What your function is now is x plus 3 over x plus 1. That's your new function. That's the one we'll be graphing because we got rid of the common factors. And even here, ratio of leading terms would be 1. So that hasn't changed any. Next, what else might we need to know? X and Y intercepts. So let's do them in that order. It doesn't matter. x-intercept and y-intercept. Now, what can you tell me about x and y-intercepts? One thing, they are points, and points are ordered pairs. Now, what can you tell me is special about an x-intercept? Always true about an x-intercept. Y is 0, so you can fill that one in right there. Y is 0. And what can you tell me about y-intercept? X is 0. You can fill that part in. Boy, this is easy, isn't it? Okay? Now, what is it that's going to, okay, when y is equal to 0, that's going to be your x-intercept. And what is your y? I don't see a y on the board right now except right there and right there. I don't see any y's associated with the function. So what is y? Oh, there it is. Y is f of x. Okay, now what's going to make that f of x equal to 0? No, that would be down here, the y-intercept. Well, what? Say again? Yeah, I set this thing equal to 0, and how can you make that equal to 0? What will do it for you? If you have a fractional form, something over something, let's say n over d, where did I get those letters? N over d, what's going to make that ratio 0? The only way that could be 0. If you have a fractional form, n over d, what's going to make that equal to 0? The n has got to be 0. That numerator's got to be 0. You don't want the denominator 0. We've already dealt with that. It can't be 0. But if the numerator is 0, that fraction is 0. That value is 0. And what makes that numerator 0? What value for x? -3. So that's what we fill in here. -3. All right? Now, you already got to it. What makes the y-intercept? X equals 0. Where's the best place to plug that in? Either your original, and if you did it there, what would that be? If x is equal to 0, that would be 0, and these two would be 0, what would that be? That would, say again? 3. If you put those equal 0, what would it be? 3. So I think that the y-intercept is going to be 3. Okay? We've got just about all we can from this. Let's go on and plot our graph. Okay? Let me tick off a few points. Really making them mad. I'm ticking them off. Okay? Okay. Now, what do you want to plot first? I really don't care too much what you want to plot first. Vertical asymptote. How do we do a vertical asymptote? A vertical line, where? At x equals -1. There it is. Does everybody see that? Vertical asymptote x cannot equal -1. Now what does that mean? It means this function that you're going to graph cannot touch or cross that line at all. It can come close, but it can never touch it or cross it. Okay? Next. Horizontal asymptote. And where's that? Where y is equal to 1, and you do a line there too. Now what's different about that one? The function can touch or cross it down in here, but in the long run, that's where it's heading. Wherever the function is, it's heading toward this line that way and this line that way. Okay? It can touch and cross as much as it wants to in here, but in the long run, it's okay. Now, next. Oh, let's plot those two intercepts. And what's the first one? -3, I think there it is, right there, isn't it? I can tell you the graph of this part of the function right now. Because from this point, it has to, in the long run, go to the horizontal asymptote, and the closer it gets here, it's going to go down here. No question about it. Okay? It's got to go in that direction. Okay? How about the x-intercept? Where is it? Negative. I just did that one. I'm sorry. Y-intercept. 0, 3. There it is right here. No question where we're going to go here. As it gets closer to the vertical asymptote, it approaches it but never touches it. And here it's going to go toward the horizontal asymptote. But we do have a problem, don't we, Houston? Here's the problem. At x equal 3, we cannot have the function being there. So x equal 3, whatever value this would be. Let's go on and plug it in. Let's plug in x equal 3 as if we could do that. Oh, no, we can't do it there. That would give you, no, yeah, we could. That's a plus there. 3 plus 3 is? 6 over 4 would be 3 over 2. That's 1.5. So at 1.5 on the y-axis over 3 here, we have a hole in the graph. Okay? So it's coming down here toward the hole in the graph. It can't go there, and it keeps on going. Okay? So that's how we plot this one. Okay? Because we eliminated this by dividing, we still can't have x equal 3. But it's not going to be a vertical asymptote. It's going to be a hole in the graph. So once you see the y-intercept is up here at 0, 3, you know you got to be coming this way and that way, but you got to remember you got to have a hole in the graph at x equal 3. And when we plug in here x equal 3 in this form, we found out it was 6 over 4, which is 1.5, which would be right about there. So there's your hole in the graph right there. Comes down here, skips that 1 point, and keeps on going. So x cannot equal 3 and cannot equal -1. Your domain is satisfied, and everything else is too. What you think? Does it make sense? Guess what? We didn't need any test points, did we? We had one given to us here, so that tells us where to go there. One given to us here, that tells us there. But we have to plug in the one we eliminated here when we divided out the x minus 3, plug that in to what we have left to see where the hole in the graph is going to be. And there it is. Does that make sense? All right. And that's how they graphed theirs as well. If you look in the book, you can see it. And it's almost as pretty as my graph, isn't it? Don't answer that question. Okay. Now, they picked some test values. They fit the curve. Who needs them? We had it already. Even the fact that our hole in the graph is in this quadrant, that tells us it's just going to keep on coming here. Okay? Got it. Any questions? Now, everybody got it? Can I move on? All right. All right. They did additional points. We did. Oh, that was on the previous one. Okay. That was different. We're not doing slant asymptotes, but I will tell you what they are. Consider a rational function whose denominator is of degree 1 or greater. In other words, it can't be a number. It's got to be at least a linear function. Could be a quadratic, could be a polynomial. Could be a quadratic, linear, quadratic, cubic, it could be anything. Okay? The denominator is the degree 1 or greater. If the degree of the numerator is exactly 1 more than the degree of the denominator, we would normally say no horizontal asymptote, because the ratio of leading terms would be x or x squared, it's going to infinity. And it is. That's absolutely true. But if its degree is exactly 1 more than the degree of the denominator, then the function has a slant or another word for it is oblique asymptote. Okay? Because, for instance, this one, okay? We could go through and figure out everything we needed to do. Domain, x can't be -1. Vertical asymptote, x can't be -1. Horizontal asymptote, 0. No, I'm sorry. I said the wrong word. We need x-intercept. I mean y-intercept. When x is 0, that would be 0. And sure enough, it does constitute 0. But it also is a 0, x equal 1, because that numerator, as you factor that would be x times x minus 1. So x equal 1 is also an x-intercept. Okay? So x equals 0. So there's your x-intercept. The y-intercept, 0. We've already said that. Your horizontal asymptote, it doesn't have one, because the ratio of this is x. And x gets large or small, it's going to infinity. So that doesn't have a horizontal asymptote. But it does have a slant asymptote, because the degree of the numerator is exactly 1 more than the degree of the denominator. All right. How do we determine what that is? Okay? Remember our good old division? This is a division. Now, this one can be divided by synthetic division, or you can use long division, either one. And when you do that, okay, in fact, I don't want to take time doing it, but when you do that, you're going to get an x, okay, because 1 will go into 1, x will go into x squared, x times. Okay, then you go and do the things, and then you'll get a remainder. So y is equal, no, I'm sorry, it'll be x minus 2. Yeah. That will be your I'm not doing the synthetic the division. You can do it and you'll find out that's true. And when you do it, that then becomes your slant asymptote. Now, you have a remainder, that's okay, but that's your slant asymptote. X minus 2. Y is equal to x minus 2. What you do is do division. So here's what it is. To find the equation of the slant asymptote, use division. Okay? If you can, use synthetic division, which you can in this problem, but if you can't, use long division. Okay? If this is degree 2 or greater, you got to use long division. Okay? And when you do that, they don't show you the division, but when you do it, you get x minus 2 and then a remainder. We really don't care that much about the remainder. This is what we care about. That's your slant asymptote. Whatever the quotient is from that division. Okay. All right. Nice, I got it. Okay. There you are. Okay. Does anyone else come in while I was up here talking, not paying attention? Okay. All right. So that's how you find your slant asymptote. We're not doing this. You're not responsible for it. I just wanted you to see it in case you ever needed it. Okay? Now, as x approaches, increases, decreases without bound, rather than going to a horizontal asymptote, you're going to, this part goes to 0, so that means the function's going approach that line. And that's certainly what we saw over here. As x is very large, it approaches that line. If it gets very small, it approaches that line. Okay. Now, you did have a vertical asymptote, so you stuck there too. So if you, like we found our 2 intercepts here, that means the function has to be in this quadrant. Okay? Frankly, that almost guarantees you it's going to be down there as well. You probably have to do a test point to see where, but that's easy enough to do. Okay. So they want you to do that. What would be your first step? Divide. Okay? And you, again, can use synthetic division here. One on the outside and one on the inside. We're not going to do it, but let's watch them do it. They factor the numerator. Allows you to recognize the x-intercepts, because wherever the numerator is 0, which will be x equals 2 or -1. That will give you your x-intercept, just like we did before. Where's your y-intercept? It will x equal 1. There's your y-intercept. Okay. Okay. Then they say long division. This one you can use synthetic. There's no reason not to. Okay. If it was a squared or something like that, yeah, or 3x, yeah, you'd have to use long division. But if it's one you can use synthetic, use synthetic. And they tell you, they don't show you, but they tell you it's just going to be a quotient of x and then a remainder. So the quotient of x tells you your slant asymptote. That's the identity function. Y is equal to x. Plot that in there. How did they do that? Y-intercept. Oh, we didn't do y-intercept. Yeah. Okay. I'll do x-intercept. Okay. Y-intercept, when x equals 0, what's your y-intercept? Say again? 2. So y-intercept is 0, 2. Your x-intercepts are 2, 0, and -1, 0. Okay? And your vertical asymptote is x can't be 1, and your slant asymptote, we just said, was y is equal to x. Okay? All right. And that's that. Now, they say do a bunch of test points. You can, if you want to, see what you can do without the test points. So what I would have done, I would have plotted my graph, done the vertical asymptote here, the slant asymptote there. You knew it's going to be y is equal to x. That's that line, the identity function there. You got that. Now, you've got your x-intercept here at 2, 0, over here at -1, 0, and your y-intercept at 0, 2. Hey, we don't need any additional points. If you knew these 2 points, you know it's got to approach the vertical asymptote that way, slant asymptote this way. With this point right here, it tells you it's going to approach the slant asymptote that way, vertical asymptote that way. You don't need these other points. Nothing's wrong with doing them. It's perfectly fine. It just takes more time. Doesn't get you any more information except exactly where that graph goes in. So that's how you do slant asymptotes. Don't worry about them. You're not responsible for them. But in case you ever need them, there they are. Now, we are going to do applications. There are many examples of asymptotic behavior in real life. For instance, example 8 shows how a vertical asymptote can help you analyze the cost of removing pollutants from a smokestack emissions. Boy, that's hard to say. Utility company burns coal, shame, to generate electricity. The cost C, capital C in dollars, cost of removing P% of the smokestack pollutants is given by this formula. Okay? Now, that's a rational function. Not written in the way we normally think of it, but it is a rational function. Okay? And this is good for any percent from 0 to 100%. I can't think of any percents beyond that, can you? You can't have a -%, you can't have 103%, no matter what the code says, okay? But your percentage is somewhere in that thing. Notice it can't equal 100. You don't have the equal sign there. Why can't it equal 100? That would make your denominator 0. So anything up to that, you can have. You can have 0 emissions, okay? No, 0% removal. That's how they used to be. You're a member of the state legislature considering a law that would require utility companies to remove 90% of the pollutants from their smokestack emissions. The current law requires 85% removal. Doesn't sound like a lot of difference, does it? Unless you have asthma, it may make a big difference for you, okay? How much additional cost would the utility company incur as a result of the new law? Now, to answer that question, you don't need to do a graph. Now, they're going to do one, but all you have to do is plug in a 90 here and here, see how much it costs there, plug in an 85 here and here, and see what it costs there, and take a subtraction, how much additional cost. It's really all you have to do, okay? It's not that bad, okay? So let's just do that, okay? The original cost, I'll call it C85, would be 80,000 times 85. Now they're using the number, not the decimal number, okay? Because P is a whole number. Divided by, and what's 100 minus 85? You want to do that quickly? 15. Okay. All right. So if you punch that in your calculator, 80,000 times 85 divided by 15. Anyone get it? 80,000 times 85 divided by 15. If you didn't have a calculator, you could do this sort of in your head or on paper maybe. 15 or 5 will go into this. Has anyone got it? What you got? A little louder.
I don't know if it's right.
Okay, that's all right. Tell me. It's a pretty big number. 453, is that what you said? Okay, $453,333.33. Okay, right? We want to get it exact. Okay. Now, what would it be if you did C90? That would be 80,000 times 90. I can do that one in my head, or on paper anyway, divided by 15, and I actually can do that too. 15 will go into 90 6 times, won't it? So now it's just 6 times 80,000. That's 400, right? 480,000, is that right? No. I must not have done that right. 15 will go into 90.
That's right, you did.
Say that again. Oh, wait. It's not 15. It's 10. It's 10. It's 10. I didn't subtract. Sorry. I knew that wasn't right. Okay. That's going to even be easier. Okay. That's a 10 in the denominator. And 10 will go into 90 9 times, and 9 times that is $720,000. Okay. So let's round the other one. Okay. It's going to cost the utility companies an additional almost $300,000, $267,000 approximately. Now, the question is it worth it? Well, how much of the additional cost of health care going to be if you, how will that be reduced if you go from this to that? It may be significant, it may not. There's a lot of moving parts here. So that's the kind of things they have to do. It's going to cost the utility company a lot, but is it going to save human life, human suffering, medical bills, that kind of stuff? Hard to say. Anyway, that's what we got. Now, that was easy to do without using graphing a rational expression, okay? So how would we do that if we were going to use the graph? Okay, here's the answer exactly like you got. $453,333 when that's the cost for getting the pollution down to 85%. To get it to 90%, it's $720,000. Okay, the difference is $266,667. That's a lot of money, okay? They didn't show the graph. They've got it in your book. You can see that. It still doesn't tell you exactly. It just gives you a point there, okay? So I don't know why it's an interesting problem, and it lets you know what kind of issues are at stake, okay, if their formula is right. Okay, there is a checkpoint after every problem, including those. There's also one over here, find the minimum area. Now this may be one that would be more, let me find the most white space I can. I think that's going to be it right there. Example 9, they don't show on the slide. A rectangular page contains 48 square inches of print. Okay? 48 square inches of print. The margins at the top and the bottom of the page are each 1 inch deep. The margins on each side is 1.5 inches wide. What should the dimensions of the page be to use the least amount of paper? Okay, so here's what we've got. And they for some reason drew it landscape. I don't know why they didn't do it letter, but we'll do it the same way they did. And here we have 1.5 inches here, 1 inch there, 1.5 inches here. My drawing isn't very good. So this is 1 inch here. Okay, this is 1.5 inches here. 1 inch here, and 1.5 inches here. Okay. And the rectangular page contains 48 square inches of print. So in here you got 48 square inches. What should be the dimensions of the page to use the least amount of paper? Okay. Now, how would you do that? You want what is the question? What are the dimensions of the page? So let's call this one, what you want to call that? Maybe L. And this one maybe, what would be a good name for that? W. Would that work? Okay. Now, all right. All right. They really do a weird way of doing both of this. A is the area to be minimized, which is length times width. Okay? Now, okay, I'm sorry. This dimension they're calling X. This dimension they're calling Y. Okay? Now, what we're trying to minimize is the area of the page, the least amount of pages. We know that X times Y is 48, right? That's why they chose that. So you know this, X times Y is equal to 48 square inches. Now they're choosing to solve for x, which is fine. So that would be solve for y. Y is equal to 48 over x, right? You just divide both sides by x. And that gives you 48 over x. Now, this is the area you're trying to minimize. What is the length? The length is x minus 3, right? An inch and a half here and an inch and a half here. So this would be the area is equal to, x plus 3. X plus 3, okay? And the width of it here would be your y plus 2. But your y is 48 over x plus 2. Okay? Now, if you multiply these together, it gets a little messy, but it's doable. If you FOIL this, x times 48 over x is just merely 48. The outer is plus 2x. The inner is 146. Is that right? No, 144. 3 times 48, I think, is 144 over x. And then the last is plus 6. Okay? That is the area. Okay? Now that's really ugly. Okay? You can add those two together and you get 54 plus 2x plus 144 over x. Okay? Now, that's pretty ugly looking. Here's what they did. Probably should have done it the way they did. Let's just go on and multiply this by x here and put it over x. That'll work, won't it? And multiply that by x and put it over x. Okay? No, you don't need to do that one because you're multiplying. I was adding. Sorry about that. Okay. Now, what you've got here is a rational function. That rational function is x plus 3 times 48 plus 2x divided by x. Okay. Rather bizarre function, but that is a rational function. Now, they do it graphically and they do it numerically. Numerically is a pain in the neck because it's you have to approximate anyway. The graphical solution is not particularly easy to pick out unless you have a graphing calculator. If you have a graphing calculator, I would say follow their steps and go for it. Okay? If you don't have a graphing calculator, well, either one of them, you have to use a graphing calculator or something that will do that. And since that's not required in the course, we're going to let it go at that. If you have a graphing calculator, you can go from there. If not, don't worry about this problem. You're not going to see one of these. Let's finish 2.6 by the vocabulary. Okay? Yeah. Sorry. That was fairly useless problem. I wish I'd have paid more attention to it before I started. Okay. Vocabulary, top of page 175. Functions in the form of f of x is equal to n of x over d of x, where n of x and d of x are both polynomial functions, and d of x is not the zero polynomial, are called blank blank. Rational functions, perfect. Okay. Number 2, when f of x approaches plus or minus infinity, that's when the function, the y value approaches plus or minus infinity, as x approaches A from the left or the right, x equal A is a blank blank of the graph of F. Say again? No, it's F, vertical asymptote. Okay? That's the vertical asymptote. When f of x approaches B, as x approaches plus or minus infinity, then y equal B is a horizontal asymptote of the graph of F. Number 4, for the rational function f of x equal n of x over d of x, if the degree of n of x is exactly 1 more than the degree of d of x, then the graph of F has a slant or oblique asymptote. Okay, good. Homework exercises, either 5 or 7. They're both at Calc Chat. 7's at Calc View. Any of the odds 9 through 15, they're all at Calc Chat. 15's at Calc View. Any of the odds 17 to 37, there's a whole bunch of those. They're all at Calc Chat. 27's at Calc View. I would do all of 39 to 42. Now, only the odds have answers in the back and at Calc Chat, but you should be able to pick out all 4 of those. It's just matching. Okay? Do either 43 or 45. They're both at Calc Chat. You don't need to do 47 through 59. Okay? If you've got a graphing calculator, you can do 61 or 63. Even if you don't have one, you might still be able to do those, but don't get bogged down with them. Okay? I think you can do 65 or 67. I know you can do 65. 67, don't sweat if you don't want to. 69 is a recycling problem, which is a lot like the utility problem. Okay, so you can look at that if you'd like. Then you have page design, which is similar to the one we started to do. If it's that complicated, forget it. But if it's simpler, you can certainly do that. Average speed, 73, should be one you could do. It should be at Calc Chat. True false, 75 and 77 are true false. You should be able to get those on Calc Chat. 79 is a writing problem. If that's something you might be interested in following up, you could. Hint, hint, research papers, okay. Writing a rational function, 81, you should be able to do that. That should be pretty interesting, and that's also at Calc Chat. Again, we're not doing 2.7, so skip right on through that, okay. It's not that it's not good stuff, and if any of you think you may need it in the future, by all means look at it. I don't have the PowerPoint slides out there for it, but you can still look at it. If you have any questions, feel free to ask. It's fun stuff, but we just don't have time. There is a chapter summary, and since we're doing a test on sections 2.1 to 2.6, there's almost 2 pages of summary information from 2.1 and 2.6. Some of that may be helpful to you on your, guess what? Formula and equation sheet. Remember, everyone can bring into the test a formula and equation sheet. Write down anything you want to on a piece of paper. If you need more exercise, there are review exercises at the back. None of these are at Calc View, but the odds are at Calc Chat. So you could do 1 if you wanted to. That's from 2.1. Any of the odds 3 through 7, they should be at Calc Chat. 9 should be at Calc Chat. 11 should be at Calc Chat. That's in 2.2. 13 or 15 should be at Calc Chat. 17 or 19 should be at Calc Chat. And 21 should be at Calc Chat. Then through 2.3, 23 should be at Calc Chat, 25 at Calc Chat, and 27 at Calc Chat. 2.4, 29 should be at Calc. Oh, that's one that requires complex numbers. You don't have to do that unless you just want to review it. Same with 31 and 33. Same with 35. Same with 37. But you might want to take a look at 39. It will have some complex solutions, but you just see what that looks like. So not many of those would be necessary. 2.5 though, 41 should be at Calc Chat, 43 at Calc Chat, 45 at Calc Chat, and 47 at Calc Chat. And 2.6, 49 at Calc Chat, any of the odds 51 to 57 at Calc Chat, 59 at Calc Chat for seizure of illegal drugs, and that's all of those. The chapter test, I believe all these answers are in the back, and you can certainly do Calc Chat for the odds of those as well. I wouldn't worry with 11 9 or 11. Okay? This is on the chapter test, page 192. And don't worry with 17. Because but the others are at Count Chat. There's a blurb here on proofs in mathematics if you want to do that, and another one on problem solving. You certainly can do that. Now, how much time do we have? Not much. So let's get out of this. I wish I hadn't wasted any time on example 9. Okay. We have 3 minutes. Let's see what we can introduce in 3.1. We'll pick this back up the Monday after Thanksgiving. All right. Now, we've looked mostly at polynomial functions, rational functions, okay? Now we're doing 2 more kinds of functions, exponential functions and logarithmic functions. Now, you might say, wait a minute, with polynomials we had exponents, didn't we? And that's certainly true. We'll see, look at these pretty interesting looking examples there. 3.1 is exponential functions and their graphs, okay? We're going to recognize and evaluate exponential functions with base A. We'll graph exponential functions using a one-to-one property. We'll recognize, evaluate, and graph exponential functions with base E. And we'll use exponential functions to model and solve some real-life type problems. And believe me, they do. They're very, very handy. So what in the world is an exponential function? Well, what we've dealt with so far, polynomial functions, rational functions, these are all forms of algebraic functions, okay? But in this chapter, we'll study 2 types of non-algebraic functions. The first is exponential functions, the second is logarithmic functions. And these functions are examples of what they call transcendental functions, not algebraic, but transcendental. Here is a difference. The exponential function with base A is denoted by f of x is equal to a to the x. Now, how did that differ from polynomial functions? In polynomial functions, your base was the variable and your exponent was the number. Okay? And those numbers could have been fractions, decimal, positive, negative, whatever. But now the base is the number, the exponent is your variable. So that's the difference. Now, we do limit the base. We don't have A ever being negative. Can't be 0 either. If that was 0, everything's 0. Okay? So it can't be 0 and it can't be 1, because if that was 1, everything would be 1. Okay? But A can be anything between 0 and 1, it's neither one of those, or anything greater than 1. And X is any real number. So that's the difference, and that's what we'll be doing with exponential functions. Okay? How are we doing on time? Are we out? Okay. We'll begin next time with the verbiage just underneath the definition. Now, next time we'll have the test. Please get your quizzes into me. And next time we'll have our test. Bring your formula and equation sheets. And it goes to this. Okay. Thank you. All right. Good deal. Thank you.
Have you graded?
Yeah, you got a 93. You want to see it? Okay. Let me get these in. So we help them. Have you got class right now? Okay. Gotta get it back. Yeah.
I had a question.
Wait, I can't let you have it. I have to have it back because not everybody turned it in.
To what grade I have it on test 1? Because I was going to finish it, but I just want to know what grade I have so far. I need to go back and have more to it.
That's one.
Okay, yeah. I'm not done.
You might finish it.
Yeah.
Good. I like the choice. They're not really cough drops, but they're ginger chews.
Nothing fun then.
Yeah, but the gingers, they're really strong with ginger, and that really helps.
I've heard of people using like ginger root when they're sick and stuff.
My younger brother likes ginger beer when he has a cold.
I've never
Of course, he likes
tasted it.
beer, but you know.
Never tasted it. You have a good day.
Thank you. You too. Any questions? All right. Good deal. I recorded.